So for this week's 2 lectures, we are going to finish Chapter 6. It is about estimation. Before spring break, we talked a little bit about estimation. And in page 4, in order to estimate a population parameter, mu, we gave 5 examples of estimators. And a fundamental question is what criteria to use to choose among them. And we introduced the first criteria we are going to use, which is called mean squared error. The definition is given in page 4, and an extension of the definition is given in the second formula of page 4. And the derivation is written in the right side of the screen. As you can see that the key point is to add a expected value of theta hat and then minus a expected value of theta hat. And then we expand the square, and it turns out that the multiplication parts becomes 0 because many of them are constant, so that you can take them out. And we give a definition called an unbiased estimator of theta. So that is to say, if a point estimated theta hat, if the expected value of theta hat is equal to the parameter theta, then we say that theta hat is unbiased estimator. And so we also review some basic definitions, such that usually we use theta hat to denote an estimator. An estimator is a random variable because it is a function of sample data, and sample data is random. And we use theta to denote population parameter, so this is a fixed but unknown. And our goal is to estimate theta using a good estimator. And we also give some basic formulas for expected value and variance. So those are the knowledge we have learned from the previous lectures. Let's look at the first example. So the first example is to estimate population proportion. So you can have some seconds, you can take some time to read those to read this example. And it is sensible to use the average of x, the average of the sample, to estimate this p. And we call it p hat. So p hat will be equal to x divided by n. And after some derivation, we know that p hat is unbiased. So why? We give the derivation in the right hand side as well. So you can see the expected value of p hat will be equal to the expected value of x divided by n. Since n is a constant, so we can take it out of the expectation. Then it will become expected value divided by n. And we know for a binomial random variable, the expected value will be equal to n times p. So finally, we get expected value of p hat equal to p. Then we conclude that this p hat is an unbiased estimator of p. And usually, we use x bar, which is the sample mean, as an estimator of the population mean, because sample mean has the good property of unbiasedness. And we also give the derivation in the right hand side. So expected value of mean will be equal to the expected value of the average of the sample points, right? And since n is a constant, still we can take this n out. And because x1, x2, all the way to xn, they come from the same distribution, so they will have the same mean. So the n will cancel out, then the expected value of x bar will be also equal to mu. And we talked about an unbiased estimator of the population mean, which is x bar. Now let's talk about unbiased estimator of population variance. And if you learned some basic statistics lectures, you will know that a very common estimator for population variance is the sample variance defined in page 8. And it turns out that this sample variance is unbiased. And we don't do proof here, but it is a good knowledge to know that the sample variance defined in this way is unbiased. So that is to use the sum of square divided by n minus 1. One thing to note that even S square is unbiased for estimating sigma square. S is biased for estimating sigma, so they don't have a 1-to-1 relationship. And now let's talk about mean and variance of the sample mean. So as we have learned that sample mean is a random variable, and it is because it is a function of the sample points, then it is sensible to compute mean and variance of the sample mean, right? Because sample mean is a random variable itself. And we have already derived a sample mean in page 9's note, and we can also derive the variance of sample mean in a similar way by applying properties of variance calculation. So the variance of sample mean will be equal to the variance of the sample average. And because n is a constant, so we can take n out, and we can take n out of the variance and make it n squared. And then we sum the variance of different random variables, because the x1, xn to xn, they are all independent. So the details of derivation is also given in the note on the right hand side. Here we give another example. So this is a uniform example. You can again pause this video and read through the problems. And first, we need to show that x bar is a biased estimator of theta, and we need to find its bias. And if we recall, if x follows a uniform distribution with parameter a, b, then the expected value of x will be the average of a and b. And as in this question, our a is theta and our b is theta plus 1. So the expected value of a random variable from uniform distribution will be theta plus 1 divided by 2, which gives us theta plus 1 over 2. And we have already shown that the expected value of x bar will be equal to the expected value of a single observation. So we derived that the expected value of x bar is equal to theta plus 1 over 2. However, in order to have a unbiased estimator, okay, the expected value of x bar must be equal to theta. So this proves that x bar is a biased estimator, and the bias is just their difference, which is the expected value of x bar minus the parameter theta. So that gives us of 1 over 2. So x bar is a biased estimator, and the bias is 1 over 2. And what is an unbiased estimator of theta? So to qualify for an unbiased estimator of theta, so the expected value of this estimator must be equal to theta. So we can rearrange the equation in the note and move the 1/2 to the left. Then we have expected value of x bar minus 1/2 equals theta. So that means x bar minus 1/2 is an unbiased estimator. And let's modify this example a little bit. So instead of a uniform distribution from theta plus 1, now we consider a uniform distribution that is over the interval 0, a. And what is x bar now? Or what is the expected value x bar now? So the expected value of x bar will be equal to expected value of a single x1, right? And we know the expected value of x1 will be equal to the average of 0 and a, which is a over 2. So again, x bar is also a biased estimator, However, if we rearrange it and move this 2 to the left hand side of the formula, then we have expected value of 2 times x bar equal to a. Then we can conclude that 2 times x bar will be an unbiased estimator of a. And a next example is about a Poisson random variable. So you can go back to the previous notes to review what a Poisson random variable is. And a very important property of Poisson is that its mean and variance are the same. And the mean of a Poisson random variable is equal to mu, and therefore the mean of the expected value of the mean of the Poisson random variable is also mu. As we can see that we can derive. So far, we already know that at least two estimators can serve as unbiased estimator of a parameter, mu, right? The first one is the sample mean. So sample mean can be an unbiased estimator of population mean. And the second is one of the sample point, right? Because the expected value of x1 will be equal to mu. So x1 can be another unbiased estimator of mu. So which estimator do we choose? Do we choose x1 as an estimator of mu, or do we choose x bar as an estimator of mu? So here we introduce the principle of minimum variance unbiased estimation. So that is to say, we can choose among all of the unbiased estimators that give us the minimum variance. As you can see, the variance of x will be equal to sigma square, right? And the variance of x bar, as we have derived, will be equal to sigma squared divided by n. So apparently, the variance of x bar will be smaller than variance of x1. That is to say, using this principle, x bar is a better estimator than x1 because both of them are unbiased, but x bar has a smaller variance. And another concept we are going to introduce is called a standard error. So standard error of an estimator measures how good this estimator is. It is defined to be the standard deviation of a random variable or of an estimator. So for example, let x1 to xm be a random sample from a normal distribution. And we know that a good estimator of population mean is just the sample mean denoted by mu hat equal to x bar. Then we have already derived that the variance of x bar is equal to sigma squared divided by n, which gives us a estimate of the standard error, standard deviation equal to sigma divided by square root of m. And typically, this sigma is unknown, and we have seen from the previous slides that s squared gives us a good estimator of sigma squared. So it is reasonable to use s to estimate sigma, and then we can replace s into the sigma. That is to say, we have a standard error of the estimator theta hat as s divided by square root of m. So let's give an example. So suppose that a random variable x follows a binomial distribution with parameter n and p. So n is known and p is unknown, and our goal is to estimate p and measure how good this estimator is. And previously we saw that p hat is equal to x divided by m. So where x is the number of observed successes, and n is the total number of trials. And we have already proved that p hat is a unbiased estimator. And now let's derive the standard error of p hat. So the standard error of the p hat is equal to the square root of the variance of p hat. And variance of p hat is variance of x divided by m. And variance of x will be equal to n times p times q. So this is a property that we have talked in the previous lectures when we learned the binomial distribution. And finally it gives us pq divided by n and take a square root. So that is a standard error of the estimator p hat. However, p and q are unknown parameters. A good estimator of p will be p hat, right, which is x bar over m. So we can calculate the estimated standard error as p hat times q hat divided by n, and then take a square root. Now let's go to another topic called bootstrapping. So whenever we have an estimator, we want to know how good this estimator is. Then we use standard error to measure how good this estimator is. However, sometimes for very complicated distributions, it is not easy to get the standard error of the estimator. So we come up with this bootstrap method. So here's how the bootstrap method works. So suppose that we have a theta hat as an estimator from a sample, right? And it gives an estimate of 21.7. And in order to get a standard error of this estimator, then we would like to replicate our estimator by sampling from the sample. Okay, in that way we are able to have capital B number of samples, and for each sample we are able to have an estimate. And then after calculating the standard deviation of that estimator, of all of the estimator, then this standard deviation serves as a standard error of the estimator. So that's a very classical way to find a standard error of an estimator when the closed form of standard error of an estimator is unavailable or very hard to get. And this method is very widely used in practice. Now let's talk about method of moments for point estimation. So we know how to estimate mu, right? A good estimator, an unbiased estimator of mu is x bar. Now what if we want to estimate expected value of x squared or expected value of x cubic? So let's introduce some definitions first. So the first definition is case population moment of a distribution. So the case population moment of a distribution is expected value of the random variable to the k. And the case sample moment is the average of the average of the xi to the k, where x1, x2, xn are the sample points. And our moment estimator is to solve the equations in the bottom of the page 18. So let me look at this concrete example in page 19. So for example, we have a normal random variable that with parameter mu and sigma square, and they are unknown. So m is the number of parameters. So because here both mu and sigma are unknown, so we have m equal to 2. And the first moment is equal to, is just the expected value of x, which is equal to mu. And what is the second moment? The second moment is expected value of x squared. And from previous lecture, we know that the expected value of x squared is equal to variance of x plus expected value of x squared, which is equal to sigma squared plus mu squared. And then according to page 18, we need to solve mu equal to x bar and sigma squared plus mu squared equal to the summation of xi squared divided by n. So by solving these two equations, we are able to get estimators of mu and sigma. And the details are also written in the note. And let us give another example of exponential. So as we all know, the exponential distribution has a mean equal to 1 over lambda. So the first moment is 1 over lambda. Then by solving the equation, we let x bar equal to 1 over lambda. Then we have an estimate of lambda equal to 1 divided by x bar. So this estimator, we call it moment estimator. And there's another one example for gamma. So recall that in gamma distribution, we have the expected value equal to alpha times beta, and variance of gamma random variable is equal to alpha times beta squared. So we can derive that the expected value of x squared will be equal to alpha beta squared plus alpha squared beta squared. And the expected value of x squared is just the second moment. So to obtain estimators of alpha and beta, we solve these two equations. And after solving these two equations, we are able to get estimators on the left-hand side of the screen. So in a word, moment method. Okay, so this is called method of moments. Method of moments provide us a way to estimate those parameters in the population. So besides method of moment, let us introduce a more widely used method called the method of maximum likelihood. And let us give a starting example. So this example, so you can have some time to read through the example. So this example is a hypergeometric example. And first we write down the PMF of the random variable. And we observe that x is equal to 1, right? X is equal to 1. And there are and because a box contains 4 balls, so theta is at most 4. And in order to have a reasonable estimate of theta, so let us just plug in every possible value of theta into the PMF and to see what their probability is. So because we observe x equal to 1, so we and for when theta is equal to 0, we get a probability 0. And again, we insert x equal to 1 and evaluate theta at 1, then we get a probability 1/2. And by inserting different values, different possible value of theta, we get different probabilities. So how do we choose among those 5 values of theta? So we choose the one that makes the probability largest. That is to say, the 3/3 are the largest probability among the 5 probabilities, and theta equal to 2 is what makes the probability equal to the largest. So we guess that. So a reasonable guess is that theta is equal to 2. So that using this criteria, so we are able to give a estimator called the maximum likelihood estimator. because this estimator maximized the likelihood. And page 22 gives formal definition of MLE, the maximum likelihood estimate. So in a word, it is an estimator that maximizes the likelihood of the data. Another example. So suppose that we have a random variable x follows a binomial distribution n and p. And n is fixed and known, but p is fixed but an unknown. And we observed a value small x. Now we want to have an estimator of p. And from previous slides, we know that a reasonable estimator can be small x divided by n, right? So that will be a reasonable estimator. But now let us use the maximum likelihood estimator, okay, to see if the maximum likelihood estimator MLE coincides with the previous estimator we have. So first, let's write down the PMF. Okay, the PMF is given in page 23, and x is given. Now we want to maximize this density, okay, in terms of p. Then let's take a log of this likelihood first. It is a convention to take a log because log is a monotone increasing function, right? So we take a log of this density. So then maximizing f will be equivalent to maximizing the log f. And we write down the log f in page 23 as well. And then in order to maximize this in terms of p, we have to get the first derivative of p and make it 0. And after that, we derived that this p hat is equal to x divided by n, right? So our maximum likelihood estimator is equal to x divided by n. And if we go back, this coincides with the previous estimate we came up with, right? So in this MLE, it is also unbiased. So far for MLE, we only considered one observation situation. Now, what if we observed multiple observations? So we use a very similar method. We use a very similar strategy, okay? Because they are independent. So the likelihood function are just a multiplication of them. So in order to obtain an MLE, instead of just maximizing one f, now we are maximizing the multiplication of those f. And a convention to maximize that multiplication is to take the log function, because log function is monotone and increasing, right? So to maximize the multiplication of f is equivalent to maximize the log of the multiplication of f. And the log of multiplication of f will be equal to the summation of log f. So let us see another example in page 25. So suppose that x1 to xn, they are random sample from an exponential distribution with parameter lambda. And we observed n values denoted by x1 to xn. The likelihood function will just be a multiplication of the likelihood. So that will give us, so it is written in page 25. And in order to maximize this likelihood in terms of lambda, so we first take a log of this likelihood, then which gives us n times log lambda minus lambda times a summation of xi. Then the first derivative gives us n divided by lambda minus the summation of xi. Then solving this equation, we have lambda equal to 1 divided by x bar. So this lambda hat is the maximum likelihood estimator of lambda from an exponential distribution. Another very classic example is the normal example. So suppose that we observe a series of observations, okay, from normal random variable mu and sigma square. Mu and sigma square are both unknown, and we would like to estimate them. And we've already learned how to estimate them using method of moments. So now we are going to use maximum likelihood estimator to see if they are different. So the first step is to write down the likelihood. Because we have n observations, so the likelihood are the multiplication of all of the densities. And then we take the log of the multiplication of the densities, and we have the small l mu z, where z is equal to sigma square. And in order to obtain a maximum likelihood of mu, we take the first derivative in terms of mu, and it is written in here. So by taking the first derivative and set is equal to 0, we can derive that this mu will just be equal to x bar. So the maximum likelihood estimator of mu will just be equal to the sample mean, which is the same as the method of moments, which we introduced earlier. Now, in order to derive a maximum likelihood estimator of sigma square, we need to take first derivative of this L with respect to z. So that gives us the derivation is written in page 27, and the results are written in sigma hat square. As you can see that sigma hat square is maximum likelihood estimator of sigma square, and this is different than the s square we used later, right? So s square is to divide the sum of squares by n minus 1. However, the sigma square is the sigma hat square is divided by n, and we know that s square is unbiased, right? But so here sigma square is not unbiased. So as we can see that both maximum likelihood estimator and the method of moment estimator in normal random variables, they are the same, right? In the page 19, we derived the method of moments method, okay, and they are exactly the same as the maximum likelihood estimator. However, they are biased. Now the last slide, okay. So one of the very important property of MLE, maximum likelihood estimator, is the invariance principle. That is to say, if we derive if we get a MLE of sigma square, then what is the MLE of sigma? The answer is that the MLE of sigma is just equal to the square root of MLE of sigma square. So that is called invariance principle, and it is summarized in page 28. So as we can see here, we have the MLE of sigma square equal to the sum of square divided by m, right? So by the invariance principle, the MLE of sigma will be equal to the square root of the sigma square hat. And similar, the MLE of mu is x bar, right? And then the MLE of mu divided by sigma will just be equal to x bar divided by sigma hat.